Conceptually, a discrete random variable has its probabilities dictated by a probability distribution. The probability distribution is the concept of how much probability each outcome of the random variable actually gets. Now, if we want to represent a probability distribution mathematically, we turn to what's known as a probability mass function. So a discrete probability distribution can be represented via a probability mass function. Every possible outcome for the random variable is assigned a particular probability mass. And so the distribution is characterized mathematically through this function, which we call a probability mass function. So probability mass and PMFs, what do both of these concepts refer to? Well, the probability distribution of X specifies how much probability is assigned to every single outcome that the random variable can take on. So all of the outcomes in the set of possible values is assigned some particular probability value. Now, we refer to that amount of probability as a probability mass, right? It's sort of the weight of probability. We can think about it conceptually as actually taking small weights and placing them at each of the different values that this discrete random variable can take on. It's sort of weighing down. And we know all of the weights are going to add up to 1, right? And we divide up that weight across all of the possible outcomes here. Now, what we can do is we can introduce a mathematical function that maps from our possible values to the probability mass for any random variable. And this function we refer to as a probability mass function, or a PMF, right? PMF for short. So for any random variable, we're going to denote its PMF using P, and then we use a subscript X, and it takes in an argument here, right? So it's a function, it's a mathematical function. P sub X takes in X as the argument. Okay. Now, if the random variable is obvious from context, then sometimes we'll just refer to it as P of X in this way. Okay, and so that's going to be if we don't need to clarify that it's X, but if we're dealing with multiple random variables, or if we want to be very specific, then we can write P sub X. Now, formally, what we're saying is that the probability that X takes on any particular value is going to be given by its probability mass function. So capital X here is our random variable. The probability that it takes on some specific value here is the probability mass function evaluated at that value. Okay. Now, very often we're going to define these as piecewise functions. And so if you're not familiar, a piecewise function looks something like this, right? So for example, we might say that the probability that X takes on some particular value is going to be 0.25 if that value is 0, 0.5 if that value is 1, and 0.25 if that value is 3. And so the way that this works here, right, if we think about this as being our probability mass function for this particular random variable, then if we want to know, well, what's the probability that X is equal to 0? We go into our probability mass function that's written here, we look up the value of 0, and we see, okay, that's going to correspond to a value of 0.25. Okay. Now, importantly, what if we wanted the probability that X was equal to 7, say? So what's the probability that X is equal to 7? Well, we go in and we look up X equals 7 and we see that it's not there, okay? And so by default, all values that are not listed here in our probability mass functions are going to get value of 0. Sometimes we might write this in sort of explicitly, right? So we might say that it's something like, say 0 otherwise, right? And you'd normally put this actually down at the bottom down here, right? But we could do that kind of thing. But if we don't write that in, then we just assume any value that's not listed gets a probability of 0. Okay? And so that is often how we will express our PMFs. So let's look at some examples here. Suppose that X is a random variable that counts the number of heads in 2 tosses of coin. What is the probability mass function of X? So what we need to do is we need to work out, well, what's the probability distribution? And then we need to write that down as a function of X. So the values that X can take on is going to be a 0, a 1, or a 2. We're tossing the coin twice. And so you could have 0 heads if you get both tails. You could have 1 head and 1 tail, or you could have 2 heads and 0 tails. Right? The sample space is going to correspond to these 4 different events that we have here, these 4 outcomes here. Right? So then we can just go through and count these up, right? The probability that X is going to be equal to 0, well, that only happens if we have 2 tails, and so that's 1 out of 4. The probability that X is equal to 1 is going to be if we have 1 head and 1 tail, so there's 2 events, that's 2 out of 4, which we express as 1/2. Finally, the probability that it's going to equal 2 only happens if we have 2 heads. So again, 1 out of 4. Okay, and so those are all of our probabilities there. And so then we can write down our probability mass function in this piecewise manner, right? So the probability mass function of x is 1/4 if x is 0, it's 1/2 if x is 1, and it's 1/4 if x is 2. Okay. Now, note, we didn't include anything else here, right? And so what we're saying is that for all other values of x, the probability is going to be 0, right? So we are implicitly saying, well, it's 0 otherwise, right? So you can write that in explicitly if you want to. And the other thing to note here, right, is our rules of probability are still applying, right? If we take 1/4 plus 1/2 plus 1/4, that's going to add up to 1 in our probability here. Okay, and so we can still sort of see that this is going to behave like a probability. But now, if we're given this function here, right? So if you were just handed this function, okay, and you were asked a question about, say, the probability that x is equal to 1, right? Well, then what you do is you say, okay, I'm going to take my probability mass function here. I take in the value of x equaling 1, and then I say that has to be 1/2. Right? And so you don't even need to know all of the information about the experiment up here. You just need the probability mass function for that. Now, if you wanted to, then you could express this probability mass function in a different way, right? So we can express it down here as this value here, where we're doing 2 choose x times 1/4. And I'd encourage you to actually look and see to make sure that you get the same value as up here, right? That you get the same expression when you look at it, right? You don't have to express it this way, but if we do express it this way, what's important for us is to clarify, well, what are the values that x can take on? Okay, and so here we're saying, well, it's going to take on this form if x is 0, 1, or 2. Okay, implicitly, what we mean is that if it's not 0, 1, or 2, then it takes on a probability of 0, right? And so you have to be looking for, well, what is the set of values that x is actually defined for? That's always going to be an important feature of our probability mass function. Okay. Second example here, suppose that y is a random variable that gives the maximum roll when we roll 2 4-sided dice. What's the probability mass function of y? So again, we need to think about, well, what are the possibilities for y? And then what is the probability that each of those takes on? We need the probability distribution here. Okay, so there are 16 total outcomes for these rolls of the die, for the dice here. Okay, and so then we think about, well, in each of these cases, what is the maximum? What can our maximum be? And we know that the maximum can be either a 1, a 2, a 3, or a 4, right? So the possible values for our maximum are going to be a 1, 2, 3, or 4, because those are the values we can roll on our dice here. Okay. Now, if we count these out explicitly, we can get the following probability mass function. Okay, and so how can we get a maximum of 1? Well, that only happens if we have a 1 and a 1, right? Any other combination, we're going to have a larger maximum. And so this is going to be 1 out of the 16 cases here. Okay. Now, how can we get a maximum of 2? Well, if we get a 1 and a 2, or if we get a 2 and a 1, or if we get a 2 and a 2, then we're going to have a maximum of 2. So there's 3, and that's our 3 out of 16. How do we get a maximum of 3? Well, if we have a 1 and a 3, or if we have a 2 and a 3, right? Or if we have a 3 and a 1, a 3 and a 2, or a 3 and a 3. Right? So there's our 5 cases, and here. Finally, how do we get a maximum of 4, right? And so the 1 and the 4, the 2 and the 4, the 3, 4, 4, 1, 4, 2, 4, 3, and 4, 4 all result in a maximum of 4, and so there's our 7 cases. Now, if you want to write this out explicitly, you can see that each of these values is 2y minus 1 out of 16, right? So if you plug in 1 here, then you get a 2 times 1 minus 1 gives us 1 out of 16. Plug in a 2, that's 4 minus 1 for the 3. You plug in a 3, that's 6 minus 1 for the 5. You plug in a 4, that's 8 minus 1 for the 7, right? So 2y minus 1 for y in any of these values here, okay? And so again, whether you do it piecewise or you do it sort of in this explicit representation here, that's going to give us the probability mass function here. And once we have this probability mass function, we simply need to plug in the value of y in order to get our probabilities. Okay, so what has to be true about probability mass functions? What are the properties that we're thinking of with probability mass functions? So from our axioms of probability, we know that we have our unitary axiom, so that's the probability the sample space is equal to 1. We have our non-negative axiom, so every probability has to be greater than or equal to 0. And we have additivity, so if we take disjoint events, the probability of their union has to be the sum of those probabilities. Now, if we express those using PMFs, these rules still have to apply. PMFs just talk about probabilities, and so all of the rules of probabilities have to apply to our PMFs as well. So what we can actually do is we can take these axioms and we can fit them into two key properties that probability mass functions need to have. The first is that they need to be bounded. Okay, so every probability mass function has to output values between 0 and 1. And again, this should make some sense, right? They output probabilities. Probabilities can't be less than 0. Probabilities can't be greater than 1. And so every PMF is going to be bounded. The other thing is that the PMFs have to sum to 1. So a valid PMF sums to 1 such that if you take the sum over all of the possible values of x here, right? So these are all of our values that x can take on. We add up the probability mass here. That has to give us a 1. And really what that's capturing is this idea of the unitary property, but it's also sort of implicitly encoding the additivity here, okay? And that's because we can add up these different values for our probability mass function. And so if we have these two properties, then it's a valid probability mass function, and all valid probability mass functions satisfy these properties. Okay, and so if we want to know is something a probability mass function, we have to make sure that it satisfies those properties. Now, this can be useful for us when we have partial information about our probability mass function and we want to work out, well, what is the full information about this? Okay, and so in this case, right, we have a random variable x. We're given this probability mass function here. Now, the trouble is that we're told that the probability at 0 is 3 times c. Probability that it's 2 is 7 times c, but we don't know what c is. And so the first question we could ask is, well, what is the value of c here? Okay, and so again, if we're thinking about what do we know about PMFs, right, the first thing that we know is that the PMFs have to fit between 0 and 1. Right? And so no matter what this is telling us, right, is that 0 has to be less than or equal to both 3c and 7c, and those both have to be less than or equal to 1. Now, if we actually sort of work from these expressions here, that's going to tell us that 0 has to be less than c, which is less than or equal to 1/3, right? And that's from working from this 3c and dividing both sides by 3. The other thing that that's going to tell us is that 0 has to be less than or equal to c, which is less than or equal to 1/7, and that's dividing both sides by 7 here, okay? And so ultimately, this tells us that c is somewhere between 0 and 1/7, and that's because 1/3 is larger than 1/7, right? And so we can sort of ignore that constraint here. So the first thing is from our boundedness, we know that that c is between 0 and 1/7, okay? Now, as long as we get a value between 0 and 1/7, we're going to be fine, right? But that's still not a specific value. And so then how else can we deal with this? Well, the other thing that we know is that 1 has to be the sum over all of our values for x of our probability mass function here, right? And so what are the values of x that we can take on? Well, we can take on a value of 0, we can take on a value of 1, or we can take on a value of 2, okay? And we know that this has to equal 1. And so as a result, if we take 3c plus 0.6 plus 7c, that has to equal 1. And what we could do is we could write this as 10c's, right? 3c plus 7c is our 10c, plus 0.6, and this is all equal to 1. Okay, and so then we could solve this equation for 1, right? We'd subtract over the 0.6, we'd divide both sides by 10, and that's going to give us a value for c. And so we can walk through that, again, this full argument here, okay? So what is the value for c? Well, all values have to be between 0 and 1 through the bounded property, and so that gives us that c has to be between 0 and 1/7. Okay, moreover, we need to have 1, which is equal to 3c plus 0.6 plus 7c, so 10c plus 0.6. And so if we actually solve for that, we get 1 minus 0.6 divided by 10, or 0.04. And so what we're saying is that c has to be a value of 0.04, okay? And so that's the value of c. It satisfies all of the properties that we need here. Now, what is the probability that 0 is less than x, which is less than or equal to 2? Okay, and so if we actually wanted to think about this event here, right, then we can think about this event as being, well, for x to be greater than 0, we can cross out 0 here, right? And so then we want it to be either 1 or 2, okay? And so as a result, we can take the probability that x is equal to 1, so that's 0.6, plus the probability that x is equal to 2, which is 7 times c, which we know c is 0.04, and that's going to give us our response here, right? So 0 less than x less than or equal to 2 is the probability that it's 1 plus the probability that it's 2, which gives us a total probability of 0.88. Okay. Alternatively, we could have used the complement rule here. Okay. And so what are we thinking about there? Well, the probability that x is between 0 and 2, right, is going to be 1 minus the probability that it's 0, right? And why is that the case? Well, we know probability that it's less, or that x is greater than 0 and less than or equal to 2 is the same as the probability that x is equal to 1 or 2. And so that's the event we're thinking about here. Well, what's the complement of that event? Complement is everything else, so that's x equals 0. And so using our complement rule, we can write that as 1 minus the probability that x is 0. So that's 1 minus 3 times c, which is the same thing at 0.88, right? And so the complement rule still applies here, even though we're working with our probability mass function. Now, when we're dealing with probability mass functions, oftentimes we'll write them piecewise. Sometimes we can write them out sort of explicitly using our basic operations, but sometimes you'll see probability mass functions expressed in alternative ways. And one of those ways is going to be expressing them graphically. And so commonly, you might see a bar chart or what we'll call a lollipop chart to represent a probability mass function. So what might that look like? Well, we might have something that looks like this. And so this could be the representation of a PMF. And again, maybe you see it like this, or maybe you would see it as a bar chart, right, where these would all be sort of thicker values here, right? So you could imagine this all being filled in as for sort of full thick bars, right, or lines themselves. It's going to represent the same general idea, okay? And so with all of that, how do we actually read this? Well, the values along our axis here are going to be the values for x, and the values along our y-axis here are the probabilities. And so here we say, well, the probability that x is equal to 0 is going to be 0.05. Probability that x is equal to 1 is 0.15. The probability x is equal to 2 is 0.2. The probability x is equal to 3 is 0.25. 4, 0.15 again, 5, 0.1, 6, 0.05, and 7 is also 0.05. And one of the reasons that we like these probability distributions expressed graphically is because it gives us a very easy visual sense of what is highly likely and what is not so likely. So here, right, really what we're thinking is, okay, well, values between, say, 1 and 4 are more likely than everything else, right? And that's sort of easy to see. It's easy to see that 3 is the most likely value for us to get, right? So all of this becomes sort of encoded within the shape of this distribution here. Okay. And so you might see it graphically. Another way that we might express these is using a table of values. And so what if we wanted to write the same PMF down using a table of values? Well, we might write something like this, right? Where here, the top row here is the values for x. And so we get a 0, 1, 2, 3, 4, 5, 6, or 7, right? So 0 through 7 here. And then going through, we find the corresponding probabilities for each of them. So 0.05, 0.15, right, 0.2, 0.25, and so forth. And so this distribution down here expressed in a table is exactly the same distribution as this one expressed up here graphically. And we could also express that piecewise. Okay, and so all of these are encoding the same information mathematically, right? Oftentimes, we're just going to write this down explicitly because that's certainly very useful for us in terms of dealing with the mathematics or algebraically manipulating these expressions. However, sometimes it's going to be more helpful to have it summarized as a table or to see it graphically. Ultimately, the PMF is going to be the mathematical representation of our probability distribution if we're dealing with a discrete random variable. Now, because it's just dealing with probabilities, it's going to satisfy all of our rules for probability, which means that working with PMFs is really not functionally different than working with probabilities that are event-based.